Good evening, everyone. Let's just wait for 5 minutes so that the people can join. Okay, let us start. I hope you all must have gone through the theory lecture videos. So we'll be doing some questions related to that theory so that you can understand them better. So today we'll be using mainly the Frobenius method to solve second order differential equations and find the series solution. So let's start with the first question. Question 1. Use Frobenius method to solve equation 2x square y double dash y dash plus x minus 5y is equal to 0 in some interval 0 to r. You can directly see that. I hope I don't need to explain it again. That x equals to 0 will be a regular singular point for equation 1. X equal to 0 is a regular singular point. If you want to know what is regular singular point, just go back to the previous lectures, you will get that. So, and hence there exists a solution pi x of the form summation n from 0 to infinity Cn x to the power n plus r, where C naught is non-zero. So this implies y dash x is equal to summation n from 0 to infinity Cn n plus r x to the power n plus r minus 1 y double dash x is equal to summation n from 0 to infinity Cn n plus r n plus r minus 1 x to the power n plus r minus 2. Now putting the values of pi, y dash and y double dash in equation first, we get 2 summation n from 0 to infinity Cn n plus r n plus r minus 1 x to the power n plus r minus summation n from 0 to infinity Cn n plus r x to the power n plus r plus summation n from 0 to infinity Cn x to the power n plus r plus 1 minus 5 times summation n from 0 to infinity Cn x to the power n plus r is equal to 0. Now here all the terms the summation is from n equals to 0 to infinity, and moreover we have x to the power n plus r n plus r n plus r. Just this one is the problematic case. So we'll just translate it. Now we know that summation n from 0 to infinity Cn x to the power n plus r plus 1 is equal to summation n from 1 to infinity Cn minus 1. We have just shifted the sum x to the power n plus r. You can see that when we'll put n equals to 0, we'll get c naught x to the power n, sorry, x to the power r. And earlier we wanted when we'll put n equals to 1, yes, when we'll put n equals to 1 here, we'll get c naught x to the power r plus 1. Here also, when we put n equals to 0, we get c naught x to the power n r plus 1. So eventually both the sums are same. So this implies, this gives us 2 times summation n from 0 to infinity cn n plus r n plus r minus 1 x to the power n plus r minus summation n from 0 to infinity cn n plus r x to the power n plus r plus summation n from 1 to infinity minus 1 x to the power n plus r minus 5 summation n from 0 to infinity cn x to the power n plus r equals to 0. Now we can see that except for 1, all the terms, in all the terms the sum is from 0 to infinity, but to make this uniform we'll take n equals to 0 separately and rest of the sum separately. This gives us 2 c naught r r minus 1. Let's take c naught common. 2 r r minus 1 minus r minus 5 times c naught x to the power r plus summation n from 1 to infinity cn times n plus r n plus r minus 1, sorry, 2n 2r minus 2 minus 1 minus 5 plus cn minus 1 x to the power n plus r is equal to 0. This gives us 2r square minus 3r minus 5 times c naught x to the power r plus summation n from 1 to infinity cn times n plus r 2n plus 2r minus 3 minus 5 plus cn minus 1 times x to the power n plus r is equal to 0. Now now equating the coefficients of x to the power r, x to the power r plus 1 and so on, we get 2r square minus 3r minus 5 is equal to 0 because our c naught was non-zero. Now this equation is called indicial equation. So let me recall what happens for the various cases of roots of this indicial equation. So now we have this second order indicial equation. We have three cases. Case 1, let R1 and R2 be the roots of this indicial equation. Our case 1 is when R1 not equals to R2. Moreover, R1 minus R2 is not an integer. In that case, we'll have to find solutions. We'll have to find the coefficients CIs and we'll get two solutions. Y1x is equal to x to the power R1 summation Cn x to the power n plus n n from 0 to infinity. Y2x is equal to x to the power R2 summation n from 0 to infinity Cn x to the power n, and our general solution yx is given by a times y1x plus b times y2x, where a and b are some arbitrary constant. Second case is when both the roots are equal. In that case, our first solution y1 is x to the power r summation n from 0 to infinity Cn x to the power n, and second, in this case C0 will turn out to be 1, and the second linearly independent solution is given by y2x is equal to x to the power r summation n from 0 to infinity some other constants dn. Here also let's take this as something else, because in both the cases the constants, the coefficients will be different. dn x to the power n plus log x times y1x. One can easily see that this y2 will also satisfy the given equation, and our general solution would be given by yx is equal to a y1x plus b y2x. And in third case, this was case 2, case 3 would be when r1 minus r2 is an integer. In this case also, similar to the one where we had repeated roots, we'll find solution y1 x as x to the power r1 summation n from 0 to infinity cn x to the power n. Then we can and y2 x is equal to x to the power r2 summation n from 0 to infinity dn x to the power n. We'll see, one can easily see that if we take only this much, then y1 and y2 will turn out to be linearly dependent. So in this case, we'll just add as done in earlier, as done in the case 2. We'll add some constant alpha times y1x times log x. One can easily see that again these y1 and y2 both will satisfy the equation, and our general solution would be given by yx is equal to a times y1x plus b times y2x. Now in this case, our indicial equation was our indicial equation was 2r square minus 3r minus 5 equals to 0. So its roots are r is equal to 3 plus minus under root 49 by 4, which will give us 5 by 2 and minus 1. Clearly both the roots are distinct. Moreover, their difference is not integral. Therefore, we'll directly get two linearly independent solution corresponding to different values of r. So taking r1 equals to, now above, by from this part we'll get, and we have Cn is equal to minus Cn minus 1 by n plus r 2n plus 2r minus 3 minus 5. Just putting this coefficient to be 0. Now we'll take case 1 when r1 is equal to 5 by 2. This is for every n greater than equal to 1. So we get Cn equals to minus Cn minus 1 by 2n square minus 7n. for every n greater than equal to 1. Or this can be written as minus Cn minus 1 by n 2n minus 7 for every n greater than equal to 1. This gives us C1 is equal to minus C naught by minus 5, which is C naught by 5. C2 is equal to C1 by 6, which gives us C naught by 30, and so on. Therefore, y1x is equal to times 1 plus x by 5. Sorry, and we also had x to the power r1. r1 was 5 by 2. This is for r1 equals to minus 1. Minus 1 x by 5 plus x square by 30 and so on. Now we'll see what happens for r equals to 5 by 2. In this case, our Cn would be minus Cn minus 1 by n plus 5 by 2, 2n plus 5 minus 3 minus 5, which is minus Cn minus 1 by n 2n plus 7. This is just basic calculation. One can easily see the in between steps. So this gives us C1 is equal to minus C naught by 9. C2 is equal to minus C1 by 22, which is equal to C naught by 198. C3 is equal to minus by 7722. Please check the calculations again, there might be some mistake. This gives us y2x is equal to C naught x to the power 5 by 2 times minus 1 by 9, 1 minus x by 9 plus x square by 198 minus x cube by 7722 and so on. And our general solution, therefore, our general solution yx is given by some other constant a, x to the power minus 1 times 1 plus x by 5 plus x square by 30 and so on, plus some other constant b times x to the power 5 by 2, 1 minus x by 9 plus x square by 198 minus x cube by 7722 and so on. So this is our general solution. I hope all these steps were clear enough. Let's move to the next question. Question number 2. Use Frobenius method to solve. start to solve. Two x square y double dash plus xy dash plus x square minus 3y is equal to 0. And some interval 0 to again clearly as following the steps as discussed in previous tutorial. One can see that x equals to 0 is a regular singular point for equation 1. Therefore, there exists a solution by x of the form summation n from 0 to infinity Cn x to the power n plus r, where C naught is non-zero. So again, differentiating it, we'll get y dash x is equal to summation n from 0 to infinity Cn n plus r x to the power n plus r minus 1, and y double dash x is equal to summation n from 0 to infinity Cn n plus r n plus r minus 1 x to the power n plus r minus 2. Now putting the values of yx, y dash x and y double dash x in equation first, we get 2 times summation n from 0 to infinity Cn n plus r minus 1 x to the power n plus r plus summation n from 0 to infinity Cn n plus r x to the power n plus r plus summation n from 0 to infinity Cn x to the power n plus r plus 2 plus summation n from 0 to minus 3 summation n from 0 to infinity Cn x to the power n plus r is equal to 0. Now again, all the terms have x to the power n plus r except for this one. So we'll just translate this sum. So we have summation n from 0 to infinity Cn x to the power n plus r plus 2 is equal to summation n from 2 to infinity Cn minus 2 x to the power n plus r. So this gives us two times summation n from 0 to infinity n plus r. Let's just club the first two terms. We'll get 2n plus 2r minus 2 plus 1 Cn x to the power n plus r plus this third term is summation n from 2 to infinity Cn minus 2 x to the power n plus r minus 3 summation n from 0 to infinity Cn x to the power n plus r is equal to 0. Now here, except for this term, rest of the terms have sum from 0 to infinity. So we'll just take first two terms of this of both the series outside, and rest of the sum would be from n equals to 2 to infinity. So this gives us n equals to 0 r 2r minus 1 minus 3 times c naught x to the power r plus r plus 1 2r plus 2 minus 2 plus 1 minus 3 times C1 x to the power r plus 1 plus summation n from 2 to infinity n plus r to n plus 2r minus 1 minus 3 cn plus cn minus 2 x to the power n plus r is equal to 0. So again, since c naught is non-zero, we get 2r square minus r minus 3 to 0. This is our indicial equation. And from this sum, we'll get cn is equal to minus cn minus 2 by n plus r to n plus 2r minus 1 minus 3 for every n greater than equal to 2. So let's find the roots of the indicial equation. This gives us r is equal to minus 1 plus minus under root 25 by 2, which gives us 3 by 2 and minus 1. So now in this sum we have considered this part, and we are left with this part. So we'll consider it for different values of r. Let's start. Clearly here the roots are distinct, and moreover their difference is not even integer, so we'll get different Li solutions corresponding to different values of r. So we'll start with r equals to 3 by 2. Here, now see the coefficient of c1 x to the power r plus 1. R plus 1 to r plus 1 minus 3. It is 5 by 2, 3 plus 1 minus 3. This is 5 uh, multiplied by 2, 10 minus 3, 7, which is non-zero. Now this coefficient must be 0, because on the other side of the equation we have x to the coefficient of x to the power r plus 1 is 0. Since this part is non-zero, this gives us that c1 is 0, and cn is equal to minus cn minus 2 by, just putting the value of r to be 3 by 2, will get n plus 3 by 2 2n plus 3 minus 1 minus 3, which is equal to, after small calculations, you'll get it to be minus cn minus 2 by n 2n plus 5 for every n greater than equal to 2. So this gives us C2 is equal to minus C naught by 2 into 9 minus C naught by 18. C3 would be 0 because C1 is 0. C4 is minus C2 by 4 into 13. It will be C naught by 936. C5 would be 0, and so on. We can find rest of the coefficients. So we'll get y1x is equal to c naught x to the power r is 3 by 2 times 1 plus 0 plus c2 times x square, which is minus x square by 18 plus 0 plus c4 times x to the power 4, so that would be x to the power 4 by 936 and so on. Similarly, we'll see what happens for the case r equals to minus 1. For r equals to minus 1, again r plus 1 times 2r plus 1 minus 3 would be minus 3, which is not equals to 0. This gives us that C1 is equal to 0 and Cn is equal to minus 2 by n minus 1 to n minus 3 minus 3, which is minus Cn minus 2 by n to n minus 5 for every n greater than equal to 2. This gives us C2 is equal to minus C0 by 2 minus 1, which is C0 by 2. C3 will be 0 because C1 is 0. C4 is equal to minus C2 by 12, which is minus C0 by 24. Again C5 would be 0. C6 would be minus C4 by 42, which is C0 by 1008. C7 would be 0 and so on. Therefore, y2x is equal to C0 x to the power r minus 1 times 1 plus 0 plus x square by 2 plus 0 minus x power 4 by 24 plus x power 6 by 1008 and so on. Therefore, our general solution is given by yx is equal to a times some x to the power 5 by 2. What was their first solution? Not 5 by 2. R1 was 3 by 2. 3 by 2. 1 minus x square by 18 plus x power 4 by 936, so on, plus some other arbitrary constant b times y2x, x power minus 1, 1 plus x square by 2 minus x power 4 by 24 and so on. So this is our general solution. I hope all the steps were clear enough. Let's move to the next question. Number 3. Solve the differential equation. X square y double dash minus x y dash minus x square plus 5 by 4 y is equal to 0. Let's number this as 1. Solution. Clearly, again you can see that X equals to 0 is a regular singular point. This implies there exists a solution by X of the form summation n from 0 to infinity Cn x to the power n plus r, where C naught is non-zero. This implies y dash x is equal to summation n from 0 to infinity Cn n plus r x to the power n plus r minus 1. Y double dash x is equal to summation n from 0 to infinity Cn n plus r n plus r minus 1 x to the power n plus r minus 2. Now putting the values of y dash and y double dash in equation first, we'll get summation n from 0 to infinity Cn n plus r n plus r minus 1 x to the power n plus r minus summation n from 0 to infinity Cn n plus r x to the power n plus r minus summation n from 0 to infinity Cn x to the power n plus r plus 2 minus 5 by 4 summation n from 0 to infinity Cn x to the power n plus r is equal to 0. Now this summation n from 0 to infinity Cn x to the power n plus r plus 2 can be written as summation n from 2 to infinity Cn minus 2 x to the power n plus r. So this gives us summation n from 0 to infinity Cn n plus r n plus r minus 1 x to the power n plus r minus summation n from, let's just club for first two terms, we'll get summation n from 0 to infinity n plus r n plus r minus 1 minus 1 Cn x to the power n plus r minus summation n from 2 to infinity Cn minus 2 x to the power n plus r minus 4 summation 0 to infinity Cn x to the power n plus r is equal to 0. Taking out the first two terms of the series, we'll get, putting n equals to 0, this can be replaced by minus 2. N equals to 0, we'll get r minus 2 minus 5 by 4 C naught x to the power r plus, putting n equals to 1, we'll get r plus 1 r minus 1 minus 5 by 4 C1 x to the power r plus 1 plus summation n from 2 to infinity minus 5 by 4 times Cn minus 2, sorry, Cn minus Cn minus 2 times x to the power n plus r is equal to 0. So from here we get r square minus 2r minus 5 by 4 equal to 0, and Cn is equal to Cn minus 2 by n plus r, n plus r minus 2 minus 5 by 4. So let's find the roots of the integral equation. R is equal to 2 plus minus under root 4 square minus 4 minus 5 by 4 by 2, which is 2 plus minus. Now this gets cancelled out. We're left with 3 by 2, which is 2 plus 3 5 by 2 and minus 1 by 2. We can see that the difference of the two roots is integral, because if we take r1 to be 5 by 2 and r2 to be minus 1 by 2, we get r1 minus r2 to be 3, which is an integer. So this is this is our third case. So here our solution will be of the form this. So let's find y1 and y2. Firstly, let y1, let's take the case r1 equals to 5 by 2. Now let's start with the coefficient of c1. R square minus 1 minus 5 by 4 is equal to 25 by 4 minus 9 by 4, which is obviously non-zero. This implies C1 is 0. And we have putting the value of R, we get Cn minus 2 by n plus 5 by 2 n plus 5 by 2 minus 2 minus 5 by 4. This will be Cn minus 2 by times 4 2n plus 5 2n plus 5 minus 4 1 plus 1 minus 5, which is 4Cn minus 2 by 4n square 2n plus 10 plus 12n, which is Cn minus 2 by n plus 3. So this gives us C2, yes, C2 is equal to 2 times 5, C3 is equal to 0, C4 is equal to C2 times 4 times C2 by 4 times n plus 3 would be 7, which is C0 times 4 into 2, 7 into 5. C4 would be 0, sorry, C5. And so on, we can see that C2n would be C0, 2 times 4 times 6 and so on up to 2n. x would start with 5, 7, 9, so on up to 2n plus 3. And c2n minus 1 would be 0. So we can write y1x is equal to c0 x to the power 5 by 2 1 plus summation n from 1 to infinity x to the power 2n by this time 2 into 4 and so on up to 2n times 5, 7, so on up to 2n plus 3. Now let's find y2. So r2 is equal to 5 by 2 minus 1 by 2. Now let's see the coefficient of r1. That was r square minus 1 minus 5 by 4. So this is 1 by 4 minus 5 by 4 minus 1, which is minus 2, clearly non-zero. This implies that c1 is again 0 and we have so putting the value of r here, we get cn minus 2 upon n minus 1 by 2 n minus 1 by 2 minus 2 minus 5 by 4, which is 4 times cn minus 2 by 2n minus 1 2n minus 1 plus 4 plus 3 minus 5, which is 4 cn minus 2 4n square 6n minus 2n sorry, this is minus 1 minus 2 minus 5 4n square plus minus 10n minus 2n minus 12n minus 5 plus 5n minus 5. So this will be equal to cn minus 2 by n minus 3. So this gives us c1 0, c2 c0 by 2 into minus 1 minus c0 by 2 into 1. C3 is again 0. C4 is 2 by 4 into 1, which is minus C0 by 2 into 4 times 1. C5 is again 0. C6 would be C4 times 6 times 3, which is again minus C0 times 2, 4, 6, 3, 1. C7 is 0 and so on. We'll get C2n is equal to minus C0 2, 4, so on up to 2n 1, 3 up to n minus 3 2n minus 3 and C2n minus 1 would be 0. This gives us that y2x. What was y2x? Summation x to the power r2 summation cn x to the power n from 0 to infinity plus y1 x times ln x. So this is x to the power, what was r2? R2 is minus 1 by 2. C naught 1 minus x square by 2 minus x power 4 by 8 minus summation n from 3 to infinity x to the power 2n by 2, 4, so on up to 2n, 1, 3, so on up to 2n minus 3 plus y1x times ln x. And our general solution would be given by, general solution is y is equal to 8 times y1x plus b times y2x. I hope all the steps were clear enough. Let's move to the next question. Solve x y double dash plus x plus n y dash plus n plus 1 y equals to 0, where n is not an integer. Solution. Clearly again, we can see that x equals to 0 is a regular singular point for this problem. Regular singular point. Therefore, there exists a solution yx. This time we'll not take some in n because we already have an n in our problem. So let's take it something else. As let's take it as m from 0 to infinity. Cm x to the power m plus r. So this gives us y dash x is equal to summation m from 0 to infinity Cm m plus r x to the power m plus r minus 1 y double dash x is equal to summation m from 0 to infinity Cm n plus r, this is m plus r minus 1 x to the power m plus r minus 2. Now putting the values of y dash and y double dash in equation second, we'll get summation m from 0 to infinity Cm m plus r minus 1 x to the power m plus r minus 1 plus summation n from 0 to infinity Cm m plus r x to the power m plus r plus n times summation m from 0 to infinity Cm m plus r x to the power m plus r minus 1 plus n times summation m from 0 to infinity Cm x to the power m plus r. Let's keep it n plus 1. So let's make all the sums x to the power m plus all the sums in the form of x to the power m plus r. So we have summation m from 0 to infinity Cm m plus r m plus r minus 1 x to the power m plus r minus 1 is equal to, we'll take some other variable k to be m minus 1. So k would be from minus 1 to infinity. Okay, firstly let's just club the terms with the power m plus r and m plus r minus 1. Then that would be a bit better way to solve it. So this gives us summation m from 0 to infinity. Let's take m plus r common. M plus r minus 1 plus n Cm x to the power m plus r minus 1 plus summation m from 0 to infinity m plus r plus n plus 1 x to the power m plus r is equal to 0. Now summation m from 0 to infinity m plus r plus n minus 1 Cm x to the power m plus r minus 1 is equal to, let's take some k is equal to r minus 1. So we'll get summation, not r minus 1, m minus 1. Summation k from minus 1 to infinity. M is k plus 1. So this is k plus r plus 1. M is k plus 1. So we'll have k plus r plus n. C m is k plus 1 x to the power k plus r. So, and in the next step, we'll just replace k by m. So we'll get summation m from minus 1 to infinity m plus r plus 1 m plus r plus n c m plus 1 x to the power m plus r plus summation m from 0 to infinity plus r plus n plus 1 x to the power m plus r is equal to 0. Let's take out the first term of the first series so that rest of the sum is from 0 to infinity. We'll get, putting m equals to minus 1, we'll get r plus n minus 1 c naught x to the power r minus 1 plus summation m from 0 to infinity. This with this term we had cm cm m plus r plus n plus 1 cm plus m plus r plus 1 times m plus r plus n c m plus 1 x to the power m plus r is equal to 0. So from here we get r plus n minus 1 is equal to 0 and cm plus 1 is equal to minus cm times m plus r plus n plus 1 by m plus r plus 1 m plus r plus n for every m greater than equal to 0. So this gives us either r is equal to 0 or r equals to 1 minus n. Now since n is not an integer, 1 minus n is also not an integer. Therefore the difference between the two roots is not integral. Therefore we have two distinct roots and their difference is also not integral. We'll get linearly independent y1 and y2. So let's start with r is equal to 0 case. In this case, we have cm plus 1 is equal to minus cm m plus n plus 1 by m plus 1 m plus n for every m greater than equal to 0. This gives us that c1 is equal to minus n plus 1 c naught by n. C2 is equal to minus c1 n plus 2 by 2 times n plus 1. C3 is equal to, which is equal to n plus 1 c naught n plus 2 by 2n n plus 1. So this n plus 1 gets cancelled out. We're left with n plus 2 by 2n c naught. C3 is equal to minus c2 m is equal to 3 plus 1 4 n plus m is equal to 2, so n plus 3 by 3 times n plus 2, which gives us minus n plus 2 c naught n plus 3 by 2 into 3 n into n plus 2. So this n plus 2 gets cancelled out. We are left with minus c naught n plus 3 by 3 into 2n. Till now you must have got the pattern. So from here we can say that Cn is equal to minus 1 to the power n. Let's not write it as n. m. m n plus m c naught by m factorial times n. Therefore, y1x is equal to c naught 1 minus n plus 1 by n x plus n plus 2 by 2n x square minus n plus 3 by 3 factorial n. Is this just n? No. X cube and so on. Now let's see what happens for the case R2 equals to 1 minus n. We had so putting the value of R to be 1 minus n, we get minus Cm m plus 1 minus n plus n plus 1 by m plus 1 minus n plus 1 m plus 1 minus n plus n. Sorry. So this n gets cancelled out here also. So we are left with m plus 2 minus Cm by m plus 1 m plus 2 minus n. This gives us C2 is equal to C1. C1 is equal to, here we have m is equal to 0 minus 2 C naught by 2 minus n. C2 is equal to for C2 we have m is equal to 1, so this is minus 3 C naught by 2 times 3 minus C1 times, which is 3 into 2 times C naught by 2 times 3 minus n 2 minus n, which is 3 C naught by 3 minus n 2 minus n. Now C3 is equal to, for C3 we have m is equal to 2, so we have minus 4 C2 by m is equal to 2, 3 times 4 minus n, which is minus 4 times 3 C naught by 3, 4 minus n, 3 minus n, 2 minus n. which is minus 4 times C naught, 4 minus n, 3 minus n, 2 minus n. So till now you must have got the pattern. So on, we'll get Cm is equal to minus 1 to the power m times C naught. Sorry, this is m plus 1. M plus 1 by m minus n, m minus 1 minus n, and so on up to 2 minus n. So this gives us y2x is equal to C naught x to the power 1 minus n, 1 minus 2x by 2 minus n, plus 3x square by 3 minus n, 2 minus n. And so on. And our general solution in this case, since we have distinct roots and the difference between the roots is not an integer, we have general solution yx is equal to some arbitrary constant a times y1x plus b times y2x, where y1 and y2 are given by this and this. I hope all the steps were clear enough. Let's move to the next question. Question number 5th. Solve the Bessel's equation. The following equation is called Bessel's equation. It is given by y dash plus y dash plus xy is equal to 0. We'll mark it as number 1. Clearly, x equals to 0 is a regular singular point. This implies we have a solution of the form y x is equal to summation r from 0 to infinity. Sorry, take it to be n from 0 to infinity Cn x to the power n plus r, where C naught is non-zero. This implies y dash x is equal to summation n from 0 to infinity n plus r Cn x to the power n plus r minus 1 y double dash x is equal to summation n from 0 to infinity n plus r minus 1 Cn x to the power n plus r minus 2. Now putting the values of y dash and y double dash in equation 1, we get summation n from 0 to infinity n plus r minus 1 Cn x to the power n plus r minus 1 plus y dash summation n from 0 to infinity n plus r Cn x to the power n plus r minus 1 plus summation n from 0 to infinity Cn x to the power n plus r plus 1 is equal to 0. Now let's just club the first two terms. We get summation n from 0 to infinity n plus r common. This is again n plus r, so we'll get n plus r square Cn x to the power n plus r minus 1 plus summation n from 0 to infinity Cn x to the power n plus r plus 1 is equal to 0. Now summation n from 0 to infinity Cn x to the power n plus r plus 1 is equal to, we want it to be something like summation something of the form x to the power n plus, if we replace put some m, we want m plus r minus 1. So we'll substitute n plus 1 by m minus 1 or n will substitute m equals to n plus 2. So we'll get m from 2 to infinity. C n is m minus 2, and since n is m minus 2, we'll get m plus r minus 1. So now just substituting this, replacing m by n and putting in the above equation, we'll get summation n from 0 to infinity n plus r square Cn x to the power n plus r minus 1 plus summation n from 2 to infinity Cn minus 2 x to the power n plus r minus 1 is equal to 0. This will give us, we'll take out the first two terms of the first series. N equals to 0, we'll get r square C naught x to the power r minus 1 plus r plus 1 square C1 x to the power r plus summation n from 2 to infinity n plus r square Cn plus Cn minus 2 x to the power n plus r minus 1 equals to 0. From here we get r square is equal to 0. So our roots of integral equation are 0 and 0. So we, in this case, we have same repeated roots. So this is our case 2. And in this case, a solution by x is given by a y1x plus b y2x, where y2 is of the form this. So let's just find out what will be y1, and using y1 again we can find y2, and hence the general solution. And here we have Cn is equal to minus Cn minus 2 by n plus r whole square, which is equal to minus Cn minus 2 by n square, because r is 0. Now r plus r is equal to 1, which is not 0. So the coefficient of, to make the coefficient of x to the power r to be 0, we need C1 is equal to 0. Now this gives us C2 is equal to minus C0 by 4, C3 is equal to 0, C4 is equal to minus 2 by 16, which is C0 by 64, or we can say that C0 by 4. C0 by 2 square times 4 square. C5 would be 0, C6 would be, in the similar way it will be C0 by 2 square times 4 square times 6 square. C7 will be 0, and so on. We can find rest of the terms. So we get y1x is equal to C0 x to the power, so r was 0, so nothing, 1 minus x square by 2 square, in this case we'll have a minus, plus x power 4 by 2 square 4 square, minus x power 6 by 2 square 4 square 6 square, and so on. Now we'll find the next solution, which must be linearly independent to y1. To get that, now here, if we had not put the value of r to be 0, we would have got, so from here we have c1 is equal to, c1 is 0, we have C2 is equal to minus C naught by N is 2. 2 plus R whole square. Then C3 would be 0. C4 would be C naught by 2 plus R square, 4 plus R square. C5 would have been 0. C6 is minus C naught, 2 plus R square, 4 plus R square, 6 plus R square, and so on. So in that case, our solution would have been yx is equal to C naught x to the power R 1 minus x square by r plus 2 whole square plus x power 4 r plus 2 square r plus 4 square and so on. Now if we put this yx in our given equation, our equation was xy double dash plus y dash plus xy. One can easily substitute all the one can easily find the derivatives of this yx and substitute here. We'll get this to be equal to c naught r square x to the power r minus 1. Now differentiating with respect to r, we will get d by dr of problem we had x y double dash plus y dash plus xy is equal to c naught d by dr of r square x to the power r minus 1, which is, just applying the chain rule, you get it to be y double dash plus y dash plus x times dy by dr is equal to c naught by x, just using the product rule, 2r x to the power r plus r square x to the power r log x. And therefore we'll get our second solution y2 x to be dy by dr at r equals to 0. This will be a solution, and moreover it will be linearly independent to the first function y1, and this is given by, with you, all you need to calculate is this factor dy by dr, putting value of r to be equals to 0, we'll get it to be y1 x times log x plus x square by 2 square minus x power 4 by 2 square 4 square and so on, which is basically the same as we would have directly written as y2x is equal to y1x plus log x times y1x. And our general solution, therefore our general solution is given by arbitrary constant times y1x plus arbitrary constant times y2x. Therefore our general solution is yx is equal to y1x plus b times y2x. Let's move to the next question. This is question number 6. Solve x square y double dash plus x y dash plus x square minus k square y is equal to 0. Again, x equals to 0 will be a regular singular point. This implies there exists distribution by x of the form summation n from 0 to infinity Cn x to the power n plus r. Now I'll not be solving it again. I will just tell you what will be the indicial equation. For this, our indicial equation will be k plus n, k minus n is equal to 0. Where this n is an integer. So we get k. This is, sorry, r minus k, r plus k equals to 0. So r would be plus minus k. In this case, we have two distinct roots, but their difference is integer. So this implies r1 minus r2 belongs to z. So in this is our case 3. As discussed earlier, our solution will be of this form. So I suggest you to consider both the cases, r1 equals to k, r2 equals to k, find all the coefficients, and using those coefficients find y1 and y2, and the general solution would be the linear combination of those y1 and y2. I hope you all will be able to do this yourself. Or in the next class, we'll start with discussion, and a few more questions are left for this assignment. We'll discuss that in next class. Okay then. I hope all the steps in all the problems were clear. Mainly, we have used the fact that the point zero is a regular singular point, and hence we have a solution of this form. Then we'll find derivative, double derivative of this series and put it in the given equation. Using that, we find the indicial equation, and for the indicial equation, we have three cases. Uh, for distinct roots, for repeated roots, and for the distinct roots having integral difference. In all these three, we have discussed, I think we have discussed all the three cases and how the solution will look like in all the three cases. So I hope you'll solve this last question yourself, and then two more questions are left. We'll discuss that in the next class, and then I'll start the next assignment. Okay then.